Good morning. Last time we discussed one example of Z transform. Let me rewrite the example we discussed last time. Transform. Okay, good. Right-sided sequence, and the example is xn equals an to the u times un, and we know this signal is right-sided, and the corresponding xz equals 1 over 1 minus a z to the negative 1, and the medium convergence is outside of a circle. And today we are going to discuss another one, left-sided sequence, and the xn equals minus an and un minus 1. We are going to discuss this. Can you do this by yourself? Any questions doing this by yourself? If I ask you to do this by yourself, do you know how to start? We know the definition, right? So solution xz, by definition, the sum k equals negative infinity to positive infinity xk. Now we can write n, and xn and z to the what? Forget? Negative n. And this is a left-sided signal. So that means we do not have any signal on the right-hand side. So this this summation will be from, look at this. How to draw it? Let's draw this signal first. And this signal is when n equal to 0. Do we have anything? We don't have anything, okay? When equals 0, nothing. 1, do we have anything? No, right? This is the left-sided n. So we only form n equals negative 1. So this one equals a negative a to the negative 1, and then the next like this. So negative 1, negative 2, all the way to the left. So this is the left-sided signal. Right? So the summation will be equals from n equals negative 1 to negative infinity, and negative an and z to the negative n, like this. Any questions on it? And we don't like negative numbers here. So are we going to rewrite this one positive from n to negative 1 to positive infinity, and the there's negative sign here, so I move aside, and this one will be a, change to negative n, this one just change to a positive n. Okay? And this one will be equal to, I still want to start from 0. So 0, when n equals 0, this term equals 1. So I will put 1 here. Then minus n from 0 to infinity, a to the negative n. And I will write z over a and to the n. Then we do this. Can we sum this? This is a geometric sequence, right? Okay, the first term equals first term when n equals 0, that equals 1, and 1 minus z over a, right? And this one simplify will be equal to 1 over 1 minus a times z to the negative 1. And for us to get this result, the q or z over a must be less than 1. So the z over a must be less than 1. That means the absolute value of a must be less than the absolute value of a. The absolute value of z must be less than the absolute value of a. Question on this? I will copy this result here. Can you compare this result with the one we discussed last time? Any comment? Same, right? Alright, so let me write this, alright, erase this, and copy this one. So actually it is this, 1 over 1 minus a z to the negative 1. So the same as this, but the only difference is the region for convergence. Z must be less than the absolute value of a. Alright, so now we can I erase all this? This is just step. Okay, so any questions for this? I erase this is solution. And we need to memorize this. This is just like the typical Laplace transform pairs. So we need to memorize this, then we can easily do a lot of z transform. Okay, next example here is the signal xn equals negative 1/3 to the power of n un and minus half to the n un minus n minus 1. What is the z transform for this signal? Anyone want to discuss how to do this? We want to use a linear property, right? So we have two terms here, so we can do one term by one term. So we do this first, then we do the second term second, then we add up together. Make sense? All right, now what's the, so we can write this. Okay, this is xz. Then xz equals, we do this first, then we do this second. What is the z transform for the first one? Look at example 1. Anyone?
1 over 1.
Okay, 1 over 1 minus.
It won't be minus because it's negative.
Negative. Okay, so 1 minus negative 1/3 plus 1/3.
Minus 1.
Huh?
Minus 1.
Z to the minus 1, right?
Okay.
Okay, so the z to the negative 1. Is this done for the first part? Okay. And we need to have the region of convergence, but we'll consider later time, right? The region of convergence for this one is this is the right-sided signal, so it is outside of a circle. Okay? So the region of convergence for this is the absolute value greater than 1/3. Right? The absolute value of A is negative 1/3, so that's 1/3. Right? So this one is here. And then we have look at the compare the second part with the second example. Negative A to the n, so this is negative, so already negative. So that means we need to have a plus here. Right? And what's the result here? Again, 1 over 1 minus 1/2 z to the negative 1. And the region of convergence for the second term is
The absolute value of z is less than.
less than half, right? Then we need to combine these two regions of convergence. So what's the region of convergence? We need to find the overlap. Greater than 1/3, less than 1/2. So the region of convergence will be 1/3 less than z and less than half. This is the region of convergence. Any question? Okay, let me ask you another one. If I change this one to left side, negative n or something, and change this one to right side, what is the result? Which part we should change the result? For example, this one is negative n minus 1. This one is positive n.
Repeat that again.
I change this one to a negative n minus 1. From a right-sided signal to a left-sided signal. And I change this one from negative n minus 1 to a positive n. From negative side, from left-sided signal to a right-sided signal. So what I do not change this a, do not change this a. So what are you going to modify your answer? The region of convergence, right? So this part is still same, except that maybe there's a positive sign here. This one is positive here. So everything, if there's a negative sign here, positive sign here, and this one changed to negative 1 minus 1, this one changed to positive 1. Then we are going to have exactly the same result here, but the region of convergence will be what's the region of convergence in that case? Huh? Will be greater than 1/2 and less than 1/3. So what is it? Nothing, right? We cannot have any region. We don't have any region of convergence because there's no overlap. Keep in mind, the region of convergence must be connected. So if you have like this, you said it's greater than this, 1/2, and less than this, 1/3, then you're going to have two separate areas. So that's not going to happen. So if in that case, you can write this one, but the region of convergence is nothing, so that means it does not exist. Okay? Make sense? But in our example, it is outside of the small circle, but the inside of the big circle. So we are going to have a ring like this. So in this example, it will be like this. This is 1/3, this is 1/2, less than 1/2, and greater than 1/3. So we do have a region of convergence for this part. Question on that? If another change is, I do not change this function. I don't change this function. I only change this one, for example, to negative 2/3. What do you think you're going to change? Change this negative 1/3 to negative 2/3. This part is still good, except this is 2/3, right? And this one must be greater than 2/3. And this one is still good, and we do not change anything here, so this is good. Then combine this together, it's less than half, greater than 2/3. So again, we don't have any region of convergence. That means Z transform does not exist. Make sense? So keep in mind, you can see from example 1 and example 2. The same signal, different signals, right-sided, left-sided, can have the same Z transform, except they have different region of convergence. So that means once you calculate the Z transform, you need to state the region for convergence. Otherwise, it may not be correct. Okay. We need to, next one we are going to list the common Z transform pairs. Right? Z transform pairs. Right? First one is this. What is this? One, okay? You compare to Laplace transform. This one. Or if you calculate, the calculation is this times z to the negative n for all time. This one only exists when n equal to 0, or others equal to 0. So actually we have only one term, which is when n equal to 0. And that equals 1 for this. And when n equals 0, this is also equals 1. So 1 times 1 equals 1. Get this. Okay? The second one is UN. This one gives us 1 minus 1 minus z to negative 1, just like this. UN when a equal to 1. Go with this. And the region of convergence for this one, any z. Right? Any z is good, because this is not function of z anymore. And this one, the z must be greater than, the absolute value must be greater than 1. And we have negative left-sided this one will be the same, 1 over 1 minus z to the negative 1, but the region of convergence is less than 1. Now, the next one is n minus m. Impulse function delayed by m time. What is this? If you recall the Laplace transform, that will be still equals this thing. The z transform of this is delta function, which is 1. Then we need to multiply by exponential. So exponential here, and we don't have exponential. In Laplace transform, we need to e to the negative t sub 0 times s, right? That's Laplace transform. Here, we do not have this. Instead, we are going to have z negative m. And then this line is gone here, so that's equals this. The other two are this one, right? Next one here, this one is here, and all these are, better memorize this. The next one is n times a to the n u. So multiply by a time in time domain. This one will be and az to the negative 1 and 1 minus az to the negative 1 and square. And the region of convergence, can you specify the region of convergence for this one? Look at this one. This is right-sided signal. I'll let you give you a hint. It's z something to the a. So what is the region of convergence? Here is the conclusion. For right-sided signal, the region of convergence is always outside the circle. The left-sided signal, the region of convergence is always inside of the circle. Right? So this one will be greater than this. Make outside. And we have some cosine functions, sine functions. Cosine functions multiplied by exponential, and sine functions multiplied by exponential, and everything is in the table in the slide. Right? There's no need to list everything here. It's quite lengthy. Right? So any question on this? We need to know how to get this, like the example over there. We can start from a definition, but easier way is just familiar with this. Better is just memorize this, and then we can use all this to solve other problems. Any questions on this? Next one, we are going to discuss the properties. And this is common Z transform pairs. And next one is properties. First one, linearity. That is easy to understand. If we have A times x1n plus B times x2n, this gives us just like the Laplace transform. Give us A times x1z plus B times x2z. First one. Then time shifting. X and n minus n0. This one will be equals just xz, just like the example here. Then multiply by z to the negative n sub 0. Next is the scaling in z domain. Scaling in z, and is z to the n, z 0 to the n, and xn. This gives us a capital Z and z over z0. Next is differentiation. N times xn multiply the sequence with the n, with the time. This gives us differentiation in the Z transform. So it will be dxz dz, and we need to multiply by z, and then there's negative sign before that. And do the differentiation first then multiply by negative z. Again, we have some other properties, but not that common. These are the most useful ones. Let me read this one.
The scaling in the Z domain, what is in the parentheses beside the second x?
This one?
The up.
This one?
Yeah.
Z0. Because you multiply by Z0 to the n, and this one will be,
So that's Z over Z0?
yes, Z over Z sub 0. Z sub 0 here is constant. We can verify this, right? Okay, for example, example here, Un, what is this? That is 1 over minus z to the negative 1, right? And z is greater than 1. Yes? Right, now let's see a to the n Un. Right? In this example here, z sub 0 equals a. Then, based on this rule, property here, we still keep the same form. So that is 1 over 1 minus z to the negative 1. Z to the negative 1 here. But we need to replace this z with z over z sub 0. So that will be z over a. That make sense? Right. May I erase? Next, we do more examples with Z transform. The region of convergence for a right-sided signal is I'll give you a right-sided signal. What is the region of convergence? Right-sided signal. The signal only are non-zero for right time. What does the region of convergence look like? Easy to memorize. Right-sided signal, the region of convergence is to the right, or the limit to the right means outside of the circle. It's good? What is the region of convergence to the left-sided signal? To the left means inside the circle. Right? Now, the next is a finite sequence. Finite sequence. Finite sequence is like, for example, x n equals, actually we have done this, right? At least very similar. This one. What is the Z transform? Let's see what this signal look like. 0, negative 1, 1, 2, 3, negative 2. How many non-zeros do we have? How to draw this signal?
First one we started,
Negative 1, then we have 1. We have 0, right? Do we have 1? Yes. Do we have 2? No. Okay, good. So we have 3 non-zero values. Here, here, and here. That's all. So the Z transform will be equal to, we have only 3 terms add up together. The first one is 1 times Z to the Z to the N. What is N? Negative 1. So that is this. Second one is the value, again, equals 1 times Z to the 0, right? Z to the 0 equals 1, so that's equal. Then the next one will be Z. Right? We know that this last time, but let's discuss the region of convergence. What's the region of convergence? Can Z equal to 1?
Greater than -1, but less than 1.
Greater than 1 to negative 1?
Greater.
Can Z equals 10?
No.
Yeah, Z equals 10, you plug into here, that's no problem, right? Can Z equals 100? It's good, right? Can Z equals negative 100? No problem, right? Can Z equals 0? Is it good? This is 1 over Z, right? Can Z equals 0? No. Can Z equals infinity? Okay, if Z equals infinity, then this one equals infinity. So the region of convergence for this one is Z cannot be equal to 0, right? Not equal to 0, and not equal to infinity.
Why can it not equal 0?
Because this one here, 1 over Z, this one equals 1 over Z. If your Z equals to 0, it's 1 over 0. Again, equals infinity. Right? So when Z equals 0, this one, this term not working. And when Z equals infinity, this term is not working. All other numbers, all other Z values will work.
How about negative?
Negative infinity, yeah, positive infinity, negative infinity, the same thing. Because this is absolute value. Right? So infinity doesn't matter. Right? Negative, positive. Any questions? Okay. So this example gives us the region of convergence for a finite sequence is the whole plane, but maybe cannot be 0 or cannot be equals infinity. Okay, let's do this. If the value is like this, what's the region of convergence? Can Z equal to 0? Can Z equal to 0 for this one? Remember the definition times Z to the negative N. For this example, this N only be positive, maybe 1, 2, 3, 4, but anyway, it's finite, right? From a positive number time to positive time. So this one will be negative, for example, 1, negative 2, something. So we are going to have some terms like 1 over Z and 1 over Z to the square or something like this. So that means Z cannot be equal to 0, right? But can Z equal to infinity? z can equal to infinity. If z equals to infinity, this part equals 0, this part equals 0. So that's fine. So for this, for all positive time finite sequence, the region for convergence is z cannot be equal to 0. Okay. How about this one? Another example like this. Also finite, but all the values are in negative time. Then in that case, z cannot be equal to infinity. Z can be 0. But anyway, for any finite sequence, the region for convergence will be the whole plane. But maybe possible z equals 0, you need to exclude. Z equals infinity, we need to exclude. That's only possible exclusions. Okay? Any questions on this? Next one, we know we listed the Z transform of properties, the linear property and all the differentiation or something, right? Delay or something, and we can prove that. Right? Here we prove only one, the simplest one, to let you know how to prove this kind of question. We assume x1 n give us x1z, and x2n give us x2z. And the linear property is a times x1n plus b times x2n. What is the Z transform for this? We already listed the property equals a times x1z plus b times x. So how to get that? So here we are going to use the definition. So this one will be equal to here sum n equals negative infinity to positive infinity, and a x1n plus b x2n here. That is the signal. Then times z to the negative n here. And these two terms multiply by this. I use this distributive property. So this one will be equal to the sum of negative infinity to positive infinity a x1n times z to the negative n, then plus b x2n, then times z to the negative n. So just distribute this and this. Nothing fancy here. Now, this summation is linear. We know this from math. So I can do this plus then sum this. So this one will be equal to the summation a x1 n z to the negative n, then plus the summation b x2n times z to the negative n. There are some limit here. I'll just ignore this. So we just copy the same thing. From the property of this summation, this constant a can be moved outside. Right? So this a, I can move this a outside. And same thing applies to here. The b can also be moved outside because it's constant. Multiply everything. Now look at this. What is this term? Is this term equals to this one? By definition, right? So that means this one equals a times x1z, then plus same thing here, b times x2. Then you get the linearity property. Proof. Okay, all other properties can be proved in a similar way, but some may require more mathematical techniques that we don't need to do that. So this one just give you a hint how to do this from the definition. Eh? The next one is very important. We can also prove. It's very useful to prove, but we don't do that. I only list the result. Right? The detail, the proof is in the slide. The convolution. So x1 n convolute with x2 n. We can, you still remember we can do this, right? Two sequences convolute each other. We know we need to flip, then do this, right? Quite lengthy, but it's easier than in continuous time. Right? And in the test or in the homework, we have this, let you decompose one sequence into some impulses, then you use shift, then add, you get the result. Still remember that? Right? But after we discuss Z transform, we have another way to do this. For this Z transform, it will be, convolution will be Zx1z times x2z. See, we don't need to do the convolution, we just do the multiplication. So two sequence convolute each other. What we do is the first one, we calculate the Z transform of the first one. Then we calculate the Z transform of the second one. Then in Z domain, we just multiply together. That gives us the Z transform of the convolution. Then the next level will be use the inverse Z transform. Then you get this. Just like in Laplace transform. In Laplace transform, I want you to convolute two continuous time signals. What you do is you calculate the Laplace transform of the first one, then you calculate the Laplace transform of the second one, you multiply these two Laplace transforms together, then you do the inverse Laplace transform. You don't need really to do the convolution in time. This one, same thing, okay? This one is very useful for solving difference equations. Like in Laplace transform, we can use Laplace transform, inverse Laplace transform to solve differential equations. This one can be used for solving difference equations. Right? We are going to discuss next one. It's very useful, called the initial value theorem for causal signals. What is causal signal? Causal signal means there's no negative time. All the time for the signal must be positive. It's the causal signal. The initial value theorem for causal signals is if xn equal to 0 for any time less than 0, for any negative time, the value must be equal to 0. Right, let me ask, is un a causal signal? Is un a causal signal? This is a causal signal. For any negative time, the value must be equal to 0. Un is this causal signal? Huh? Can you draw this signal? Can you imagine this signal? Okay, do we have any value that for negative time? No. So is this a causal signal? Yes, this is. How about n minus 1? Is this causal signal? Again, you imagine the waveform of this signal. Do we have any value for negative time? No? Okay, good. This one is shifted to the right by 1 time, so this is a causal signal. How about this one? Okay, good. It's no. Because when n equals negative 1, we do have 1, which is not equal to 0. Okay, so this one is not causal. We only discuss causal signals in this initial value theory. If xn equals 0 for any n less than 0, then because we don't have any value for negative time, so what is the initial value? The initial value will be x0, right? Then what is x0? What is x0? Okay, this one equal to, once we know the z transform, we take the limit z goes to infinity, then that's it. This one is just limit, L-I-M-I-T, right? So limit. Any question on this? I need you first to imagine what we are talking about here. Suppose you have a time domain signal. That signal is causal. That means we don't have any value for negative time. The first possible non-zero value is x0. Right? That is the first one. It's possible. It can be 0, but possibly it's non-zero. But definitely for any left-sided negative time, the value must be 0. So we don't need to care about that. So what is that initial value? Once we are given the z transform, right? That is calculated. The z transform, you take the limit when z goes to infinity. Once you find this limit, then that is the initial value. Is it clear what we are talking about here? How do I know this is correct? All right, let's prove this. Again, we need to start from the definition. Xz equals what? The sum of xn times z to the negative n. And n equals negative infinity to positive infinity. It's good? Alright, now, because this signal is causal, we don't have any negative time. We don't need to consider that. So the first term to be considered is n equal to 0. Right? Right? So n equal to 0, this one will be equal to what? x0 and times what?
1.
Times 1. Okay, so that's it. That's the first term. What's the second term? The second term is when n equal to 1. Right? So that one will be x1 times what? Z to the power of negative 1, right? Or as you said, x1 over z. Z times z to the negative 1. Good? Now what's the next term? x2 over z squared. x2 over z squared, and so on. We can have infinite terms. What are these values? x1, x0, x1, x2, they are finite values, right? They are the amplitude of the signal. So they must be some constant, although we don't know. But they must be constant. Right? Now, let's take the limit xz, the limit z goes to infinity. What is this? You let z go to infinity. What we have? X0, that's it. X0. Because this one is constant, although we don't know, but it's constant. Z infinity, so still constant. But this one is constant. For example, equals 100. And this z goes to infinity. So what is this? 0. Right? Here, this x2 is also constant. For example, equals 1 million. This z squared, z goes to infinity. What is this? 0. You can see all other terms equal 0. That's it. And this one is what we have here. x0 equals the limit of xz when z goes to infinity. Right? That is called the initial value of the causal sequence. Any questions before we give an example how to use this initial value theorem? Everything's good? Okay. Example, I give you xn equals negative 1/3 to the n and un. I want to know what is x0. Definitely, this one is easy, right? You just plug. Can you tell me what is 1, 0? From time domain? This is exponential sequence, right-sided, and it is causal. So what is x0? Before we use this initial value theory. One over
1 plus 1/3 is b.
No. I mean this time domain value, the initial value. I didn't ask the z transform yet. You just look at the time domain signal. You can draw this, right? Eh? My question is, what is the first value? The initial value. 1, right? Okay, equals 1. We know that, right? When n equals 0, this is equal 1, this equals 1. So we know this one equals 1. Right? But we are going to use the other way, applying this initial value theorem to verify that a is 1. Right? Because we know it is 1. Okay, now what is the z transform? Because we need to use this. It is 1 over, this is the right-sided signal, right? So equals 1 minus a. What is a? Negative 1/3. So that is plus 1/3 z to the negative 1. And the region of convergence is to the right, because it's right-sided signal. It's outside of the circle. So this one here, then, based on the theory, x0 should be equal to z goes to infinity and take of xz. What is this? Right, let me rewrite this. So this one, z goes to infinity, and 1 over 1 minus 1 plus 1/3 and z negative 1. Okay, so make this. easier to see. When z goes to infinity, what is this? 0. This part equals 0. The denominator equals 1. So the limit equals 1. Oh, yeah, that is here. We know that. Any questions on that? This is trivial, right? It doesn't make sense. Why this is useful? We know that equals 1. Okay, now we have a better application on this. Alright, so let's see. Suppose we know x1 here. We know x0 equals 1. Let me ask, what is x1? What is x1 here? Suppose we don't know this, only give you the z transform. What is x1 here? We cannot use the initial value because this is not the initial value. This is the initial value, right? But we can manipulate, try to use the initial value theorem recursively and try to find x1 and x2 and x3 and so on. What is that? What we are doing? We find x0, x1, x2, x3. What we are doing here? I give you a z transform. You calculate x0, and by some way you can calculate x1, x2, x3. What we are doing? Inverse z transform, right? Give you a z transform, we calculate the time domain of the signal. So that's z transform, the inverse z transform. Okay, so initial value theorem can be used for inverse z transform. And we are going to discuss inverse z transform next time. Right? So let's see how to do that. Right? We know this easy. How to calculate x1. Right? Now let's look back at here. Xz equals x0 plus x1 divided by z plus x2 divided by z squared plus x3 divided by z cubed plus and so on. Right? That's definition. And by initial value theorem, we already calculated this one. We just take this one, the limit when z goes to infinity, so we get this one. So that means we know this. And we are given this xz. We know this. Okay, now look at this. I will move this term to the left-hand side because we know this, right? So I have xz minus x0. This is capital X, means the z transform. This is small x, means the time domain signal. And they will be equal to x1 over z plus x2 over z squared plus and so on. So x3 over z cubed, then plus all these terms. We can do this, right? Now, I will multiply by z on both sides. So this one here, multiply by z. And this one, this z will be gone, right? Right? So this one will be gone. How about this? Z. How about this? This square. Okay, and so on. Now, can you tell me? Can you find x1? Use the same technique as we use this one. How to find the x1? Okay, we know this term here, right? If you let z goes to infinity, take a limit. What is this? Right? Take the limit, z goes to infinity, right? This side, and this is also the limit, z goes to infinity. What is this? That's a constant. So what is it? Still here, right? What is this? 0. What is this? Okay, so now we are going to move all these terms, remove these terms. So x1 equals this, right? So we can find x1. Does it make sense? Can we find x2? Use the same method, right? Once we find this term, once we find this x2, we have this, right? We move this term, right? So here, we move this one to the left-hand side, okay, minus, and so this one is here, minus this here, then I multiply z again, and take the limit, this one will become, this one, take the limit, this one is only x2, and all this term will be z 0, 0, 0. So this part, take the limit, this one will be equal to x2. Once we get x2, okay, then we minus this x2, then I have this, then times z again, then take the limit, right? Then we are going to have this all part equals x3. So we come by this method, one by one, recursively we calculate x0, x1, x2, all values. If you use the computer code, everybody take computer language class, right? This one is just one function, recursive functions. Very simple to do this. Any question on that? All right, I'll give you an example. This is good, right? All right, let me write more for you. Right? So this one equals this. X1 equals what? The limit z goes to infinity. Hello? Xz minus x0. This one times this. Here, then take the limit, right? Is this correct? All right, I list these two for you here. Right? Example, xz equals 1 over 1 minus z to the negative 1. Question is, what is x1? You calculate this. You don't need it. Do exercise. Review the syllabus. Right? There are rules for this. you need to calculate x0 first, right? What is x0? 1. Somebody already calculated for you. Okay, so now you calculate x1. Anyone else get 1 for x0? Okay, and now try x1. You get your result, let me know. But you need to keep the limit. So you need to simplify this term. Keep the limit, right? Or you need to keep the limit.
So,
Because x1 must be a value. You cannot have z. Because this is time domain, right? Either have 1, 2, 3, 4, or 100, or any number. Must be a number. Not necessary, because there's a term here, there are also term here. So you need to combine every term together. Consider as one function. Okay. The limit is in where? It's K1 or?
Yeah.
K1, right? This one, minus 1. Okay, so what is it?
I'm just.
And then you calculate, right? This one, this. You need xz times z first, right? Something wrong?
Yeah, I'm staying in this one.
Oh, I did something wrong
Oh.
in the formula, right? Formula is not correct. I believe there must be a z before this, right? Remember this? Xz equals x0 plus x1 over z plus x2 over z squared. So what we do is we move this one. Oh yeah, right. This one more here than times z. Yeah, this is good. Yeah, this is good. You see? Okay, this is 1, not the z. That's the problem.
Hola, como me muero en sí. Tengo que.
Oh, okay. But then this one, you multiply z only on the top. You cannot multiply z on the bottom. Right? This number multiplied to this, you can only multiply on the top, cannot be on the bottom. You also multiply on the bottom because it's right? Good? Oh yeah? Anyone got the result?
Is it one?
You got one. Anyone agree with him? Okay, one is correct. Everybody got one? Not yet? Huh? You need to write your name and your ID. Okay, submit. Alright, this result also equals 1. Why this equals 1? Is this clear? What function is this? This is Z transform. What is the time domain function is this? Recall the Z pairs. What is this? UN, right? Yes? UN. So definitely equals 1. What is x2? 1. What is x3? 1. If you do all this recursively, you get all result 1. So that. Alright, submit. The next one is this is the initial value. Then what's next? You take 311. Anyone take 311 right now? Or 111? ET111. You calculate the initial value problem and what's the next one? For example, the second order circuit. The response RLC circuit. Did we discuss that in class? No? RLC circuit. Yes, right? So we have initial value, we have a all this same thing. Circuit is a system. We are this signals in the system. So we have same thing. All the techniques you learn here can be applied to the circuit. Initial value. In contrast, what's the next one? Final value. Okay, now good. The next one will be a final value theorem. We didn't discuss this, did we? In 111 or something? Second order circuit.
Been a while.
Huh?
Been a while.
Long time ago?
Yeah.
Don't tell me that. Long time ago, 111? How long have you been here?
About 2 years.
Alright. The next one will be final value theorem. This is initial value. The next one is final value. Almost the same thing. Okay, we just find the final value means the x infinity. When n goes to infinity. So we can write this one. We do not write directly like this. We said n goes to infinity, xn. What is this value? This value equal to, again, limit z goes to 1 and z minus 1 times xz. We can prove this, but I don't want to bother you. We know that. Here, I only list the theorem, and we are going to do some exercise to apply this final value. So, everybody can read this, right? You are given the Z transform xz. What you do is you multiply by x minus 1, then you take the limit z goes to 1, that limit is the final value of the time sequence. Is this clear? Okay. Let's try. Suppose the xz equals 3z squared plus plus 4 minus 3z 2z. Missed it. And divided by z cube minus 2z squared plus 1.5 z minus 1/2. This is the z transform of a time domain sequence xn. What I want is what is xn down n when n goes to infinity, final value. Maybe like this, like this, or some. Finally, it will convert to some value, or maybe like this. You know this, right? RC circuit, LR circuit, or ILC circuit. You have this kind of a response. So I want to know the final value when t goes to infinity in this continuous time. But here is discrete. So when n goes to infinity, what is xn? That is the final value. Okay, you do this. Continue on the piece of paper to this. Okay?
What does that say on the bottom after?
Here,
On the bottom after 1.5 z?
minus 0.5.
What?
0.5. You write only on one piece of paper, don't bring me two. Just continue on the first page. This actually is just the math problem, right? Try to find the limit. Anyone? Done? Almost? Almost done? Okay, almost. Good. Anyone still confused how to do this? Huh? Kind of? I'll give you this. You multiply by this one by z minus 1. Right? There's no problem for this part, right? Then you just take the limit, let z goes to infinity, goes to 1. That is our result. Make sense? Huh?
Is it 10?
Okay? 10. Anyone else close to the result? Halfway. We'll give you more time. Can you finish? Okay, everybody, write your name and your ID on this one and submit. Let's give you some bonus point. 2 questions, right? First and second.
I got those notes. I got those.
I will give you this one. Right? All right. Don't forget your name and your ID. Huh? Okay, let's have 2 minutes, 3 minutes to finish this. You know how to do this, right? You just need some time to calculate the limit. Is this the correct situation? Yes or no? Yes? Kind of?
It's been 3 years since I've taken calculus.
Oh, okay. Okay, let's do. And z minus 1 times xz equals z minus 1 times 3z squared minus 2z plus 4z cubed minus 2z squared plus 1.5z minus 0.5. Right? And we need to, looks like we need to do cancellation. Right? And that means we need to do factorization on the bottom. Right? So you need to use some technique to do the, I will put this on the top first. Right? That is 3z squared minus 2z plus 4. On the bottom, you just factorize this, and the result equals z minus 1 and z squared minus z plus 0.5. Right? This is the factorization of this one. Now we can see z minus 1, z minus 1. So we cancel this one. So this one will be equal to 3z squared minus 2z plus 4 or z squared minus z plus 0.5. Right? And we need to take the limit z goes to 1 of this. That means equals the limit z approaches 1 of this means the limit z approaches 1 of this. Now look at this. When z equals to 1, this one is not, z equals 1 is not the pole of this function. So we can directly plug z equals 1 inside here. Yes?
What is after z? Is that z plus 0.5?
This one? Yes. Because z equals 1 is not a pool of this function. Right? So the limit is very simple. You just plug z into here and that's all. So this one will be equal to z equals 1 here. So on the top that is 3 minus 2 plus 4, and on the bottom that is 1 minus 1 plus 0.5. So this one 3 minus 2 equals 1, 1 plus 4 equals 5. On the bottom 0.5, so that's why that's equals 10. That's it. Any question on that? So the final value equals 10. Means when time is large enough, this value will be, the time sequence will stabilize at 10. Now, can you tell me what is the initial value? Suppose this is causal. What is x0? What is the initial value? We don't need any phone or any calculator here, okay? What is the initial value? Zero. Okay, good, because this is the second, this is the third. So when z equals to infinity, this is second order infinity, this is third order infinity, so it's still 0. So that means the initial value equals 0, the final value equals 10. Can you imagine what is the response of the system? Suppose this is the output of the system. Can you draw what does it look like? Right? It will be like the initial value equals 0, the final value equals 10 here. This is 10. So possibly like this. You know this from circuit analysis, right? This is what circuit is this? RC circuit. Yes? We have a battery to charge this. There's R here, there's a C here. Charge this one. The response of the voltage on the capacitor look like this, right? If we have a switch here closed at the T, beginning this one equals 0, then after some time looks like this must be equals 10. Right? So this one will stabilize that to 10. So that is the system. So even we don't know what the system is, if I tell you this one is the output of the Z transform of the output, then you can imagine the system looks like this. So that is the purpose for this. Right? Any questions? Okay, thank you. That's it.